Introduction to mathematical induction. We know that the sum of first n odd natural numbers is n squared. That is 1 plus 3 plus 5 plus 2n minus 1 is equals to n squared. This is a general result. From this, we can deduce that the sum of the first 97 odd natural numbers is 9409. So how did we get that? Because we know sum of everything is n squared. So sum of first 97 odd natural numbers will be 97 squared. So n is 97. So we get this. This process of deducing particular results from a general result is called the process of deduction. The numbers 3, 2, 4, 6, 9, 2, 9, 0, 4, 5, 7, 6 are all divisible by 4. From this particular result, we can hope to have a general result that all numbers of 3 digits are divisible by 4. But this is not true because 325 is not divisible by 4. If at all this conjunction were true, we could have established its validity either by verifying the conjunction for all possible 3-digit numbers or by using some mathematical process of induction. So now the principle of mathematical induction is a mathematical process which is used to establish the validity of a general result involving natural numbers. So we have statements. So a sentence is called a statement. So we can have statements here. So you can simply say a sentence is called a statement if it is either true or false, but not both. For example, the sentence 2 plus 5 equal to 7. So 2 plus 5 equal to 7 is a statement because this sentence is true. A statement concerning the natural numbers n is generally denoted by P.N. So it's just a representation. Example: if P.N. denotes the statements n plus 1 is an even number, then P3 is equal to, so let me show it mathematically. So if Pn is n plus 1 is an even number, then P3 is what? That is, anywhere you say n, put 3. So that will be 3 brackets 3 plus 1. So that is 3 brackets 4. 3 times 4, 12, which is even numbers. And P7. So we are just testing all the natural numbers. P7 will be 7 plus 1. So 7 times 8, that is 56, is an even number. Hence P3 and P7 are both true. So if you test other natural numbers, so you will get even numbers. So this is just to test if a statement is true or false. That's what we are doing here now. This is introduction to mathematical induction. So just testing if a statement is true or false. Let's say let Pn be equals to n cubed plus n is divisible by 3. So write P1, P2, P3 and P4. So which of P1, P2, P3 and P4 are true? So now let's say P1. So anywhere you see n here, put 1. Remember, the statement here is that this result is divisible by 3. So we want to know which one is true and which one is false. So anywhere you see n, put 1. So this is 1 raised to power 3 plus 1. 1 plus 1. So this is 2. So not divisible by 3. So not true. Because the statement is that it's divisible by 3. And this is 2. So not divisible by 3. So not true. Now P2. 2 raised to power 3 plus 3. Plus 2. So 2 raised to power 3, 8. Plus 2. That is 10. Not true. Because it's not divisible by 3. Now P3 is equal to 3 raised to power 3 plus 3. So that is 27 plus 3. That is 30. So true. Because it is divisible by 3. 30 divided by 3 is 10. P4. 4 raised to power 3 plus 4. That is 64 plus 4. That is 68. So not true. Because it's not divisible by 3. So from the results, it shows that P3 only, that is P3 is equals to 30, is divisible by 3. So others P1, P2 and P3 are not divisible by 3. Hence P3 is true. So we are only testing whether a statement is true or false. So let's say another one. So this is just intro to mathematical induction. So in next video we are going to solve questions like to prove using mathematical induction. So now let's say let Pn be equals to 1 square plus 2 square up to plus n square equals n plus 1 2n plus 1 divided by 6, where n is a member of natural number. Verify that P2 and P6 are true. So now let Pn be 1 square plus 2 square plus to n square to be n plus 1, 2n plus 1 divided by 6. So where n is a member of natural number. So we want to verify if P2 and P6 are true. Now start from the left hand side. So from the left hand side, we have n square. Now this n square is called nth term. So it's this n square that will produce all this other number. So when n is 1, that is 1 square. When n is 2, that is 2 square, as it will produce this. So this is the result for the left hand side. Now for the left hand side now, sum of first 6 terms. We want to confirm it with this left hand side. Maybe it is true or not. So to verify this, we need to do the two one by one. So now verify that P2 is true first. Now we have left hand side, so P2, meaning when n is 2, sum of the first two, as in the left hand side. So we have 1 square plus 2 square, that is 2 times. That is the meaning of this P2, meaning n is equals to 2. So sum of first 2 times, so 1 square plus 2 square, so that is equals to 1 plus 4, so which is equals to 5. Now let's say the right hand side, that is n plus 1, 2n plus 1 divided by 6. So when n is 2, remember we want to do P2. We are testing if P2 is right, meaning n is 2. So if n is 2, this is 1, 2. We add the 2 together. So we want to confirm if it will be equals to if we put 2 here. So this will become 2 brackets 2 plus 1, 2 times 1 plus 1 divided by 6. So that will be 2 brackets 3 brackets 3 divided by 6. Oh, sorry, I'm put it's 2. I want to substitute. This is wrong. As in, this should be 2 times 2 plus 1 divided by 6. Remember, n is 2, so 2 brackets 2 plus 1, 2 times 2 plus 1. So this becomes 2 bracket 3. So 2 times 2, 4 plus 1, 5 divided by 6. So 2 times 3 is 6. It will cancel out this 6. So it remains 5. So this is true. So left hand side give you 5. If you sum the first two, right hand side also give you 5. So this statement is true for P2. Now let's test P6. So for P6, it means 1 square plus 2 square plus 3 square plus 4 square plus 5 square plus 6 square. So that is summation n square from n is 1 to 6. So that is we are adding everything here to 6. So sum of first 6 terms. So now 1 square plus 2 square, so that is 1 plus 4. Remember, this is left hand side, as in this. So sum of first is 1 plus 4 plus 9 plus 16 plus 25 plus 36. So everything is 91. Now right hand side, so we have n plus 1, 2n plus 1 divided by 6. So that will be 6, because when n is 6, 6 plus 1, 2 times 6 plus 1 divided by 6. So 6 cancel out 6. 6 plus 1, 7. This, and 2 times 6, 12, plus 1, 13. So now 7 times 13, 91. So is equal. So P6 is also true. So like that. So let's see another statement. So that means this is true. Let's say we have, if Pn is equal to 1 over 1 times 2 plus 1 over 2 times 3 plus up to 1 over n plus 1. So it's equal to n over n plus 1. So let's say we have this. So where n is a member of natural number, so write P2. Then confirm if this P2 is true for both left hand side and right hand side. So for left hand side, you sum the first two, that is 1 over 2 plus 1 over 6. So 1 times 2, 2 times 3. So this will becomes LCM 6. So 2 in 6, 3. 3 times 1, 3, plus 6 in 6, 1. 1 times 1, 1. That is 4 over 6, which is 2 over 3. Now right hand side, this is left hand side. So right hand side, we have n over n plus 1. So we want to test P2, meaning n is 2. So that means 2 over 2 plus 1. So that is 2 over 3. So it's true. That means this statement is true. So this video is just to test whether a statement is true or false. Now let Pn be a statement that 2 raised to the power 3n minus 1 is a multiple of is a multiple of 7. So then show that P5 is true. So we have given a statement that this is a multiple of 7. Now show that P5 is true. So meaning anywhere you say n, you should put 5. So that will be 2 raised to the power 3 bracket 5 minus 1. 2 raised to the power 15 minus 1. So that is 32767. So is this a multiple of 7? Because we said the statement is a multiple of 7. So this, if you divide this by 7, you get 4681. That means 7 times 4681. So it will give you this. So this is divisible by 7. So that means the statement is true. So hence P5 is true for these statements. So like that. So in another video now, so we are going to start the principle of mathematical induction. Then we are going to start example. So let me include the intro of the principle here. So in my next video, I will just start with example. Now principle. Principle of mathematical induction. So we short it to P.M.I. Principle of mathematical induction, P.M.I. So principle of mathematical induction. So that's P.M.I. Now the principle is that if Pn is a statement so where n is a member of natural number such that one P1 is true and 2 truths of Pk implies that implies the truths of Pk plus 1, then by the principle of mathematical induction P.M.I, Pn is true for all n is a member of natural number. Now to show if a proof is right with a mathematical induction, then these are the working rules. Working rules to apply principle of mathematical induction. So first, step 1, show that the given statements is true for first number usually n is equals to 1. So the step 1 is, if you see any question on proof of by mathematical induction, you first test the first number, that is when n is 1. That will be the first step. So you will see this in the next video, how we can use it to solve questions, to prove a already proved equation. Step 2, assume. So is all these steps we'll be writing in our proof. Step 1, we will first show that the statement is true for n is equals to 1. Then step 2, we will say assume that the statement is true for n is equals to k. So assume that the statement is true for n equals to k. Then step 3, using the assumption made in step 2, using the assumption made in step 2, show that the statement is true for n is equals to k plus 1. So now this completes the principle of mathematical induction. Conclude that the given statement is true for all n is a member of n. So if you have checked your step 1, step 2, step 3, so you have to conclude that the statement is true for all n is a member of natural number, or for any other information given. So we are going to see example on how to prove using mathematical induction in the next video. So we are going to start the working rules we are going to be using in proving by mathematical induction. So